Okay, page 7 and 8. I'm going to do both of these pages on one video. Part E, interpretation, I'm sorry, this should say interpolation, and extrapolation. Explain the difference between the two. Well, interpolating is when you take your cloud of points, and then let's say that you want to figure out what would be a data point that is in line with your data within this cloud of points. That would be interpolating. So for example, if you say, hey, I want to know what the data point that would follow this trend at this value of x, and then you'd say, oh, it will be here based on your cloud of points. That would be interpolating because you're guessing a data point within your cloud. Now, what is extrapolating? Extrapolating is when you want to figure out what the data point would be at this x value. This x value is outside of your cloud of points. And so you would guess it might be here. You don't really have as good of an idea because you don't have any of your own data points there. Okay? So the data point that's most to the left is the lower pole, and the most to the right is called the upper pole. So when you say, okay, what is the difference between interpolating and extrapolating, the easiest way to explain that is saying, okay, interpolating is guessing a data point between the two poles. Okay? And extrapolating is guessing a data point outside the poles. Okay. So it says mark the regions of the diagram at the right where you would be extrapolating. So let me erase these marks that I put. And so that would correspond to this region would be extrapolating, this region would be extrapolating. Under what conditions is it valid to extrapolate? If you read in the book, it's usually not valid to extrapolate. When it might be valid to extrapolate is if your data here between the poles is very linear. So if you have a really good linear distribution there, maybe it's okay. So let's say your data points are highly linear correlated, okay? And you have an expectation that all the data would be linear, okay? So if for some reason, based on, the phenomenon that you're measuring is a linear phenomenon, then maybe you can expect the pink regions to also be linear, and then you'll be able to extrapolate based on your cloud of points. Okay? All right. Now, we have page 7 and 8. I am going to do number 3 on page 7, and then I'm going to do the last one, which is like number 7 on page 8. Okay, I'm going to do those two problems. I'm going to skip the other two because they're kind of similar. Okay? All right. First thing, and a lot of this is, kind of repetitive. We've done the same kind of problems, but there's a couple new things, which is why I'm going to do these. Okay? All right, so number 3. Table shows the amount of time a collection of families spends preparing homemade meals each week, amount of money they spend each week on fast food. Okay. So the top one is homemade meals, amount of time they spend on homemade meals. Money on fast food is Y. Okay, so probably there's a relationship between these two. Let's see what that relationship is. So we're going to do a scatter diagram first, which we've done several times already. Let's see what the lowest and the highest number is. 2.5 looks the lowest. The highest looks to be 8.5. And then for the y value, 0 seems to be the lowest. And the highest value is 100. Okay? So the y value is going to range from 0 to 100. And the x values are going to range from 0 to, it looks like 9.1 is the highest. So it'll be from 0 to 10. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the x values is time making homemade meals, and the y value is money on fast food. Okay. Calculate the value of r. Oh, we haven't done the scatter diagram yet. Let's do the scatter diagram, at least for the, let's do some points. 3.3, comma, 85. Oops, here. 6.0, comma, 0. Right there. 4.0, comma, 60. There. 8.5, comma, 0. There. 7.2, comma, 27. There we go. 2.5, comma, 100. There. 9.1, comma, 15. Okay. 6.9, comma, 40. Okay. And 3.8, comma, 59. Okay. 7.7, comma, 29. Okay. Oops. Okay. Calculate the value of r. Okay, to calculate the value of r, we're going to put all this data into the calculator. I'm going to use, let's see, L5 and L6. So the way we're going to do this is we're going to put 3.3, comma, 6, comma, 4 into the first column. 3.3, comma, 6, comma, 4, and so on. I'm going to pause so you don't have to watch me do all this. Okay, so I just put in my X data into L5 and my Y data into L6, and now I'm going to do the stat calc to find out what the R value is. linreg, and I'm going to put second 5 and second 6 so that I can get L5 and L6 there. And then I do a calculate. And since I have catalog diagnostic on already, it shows me the R values. So the R value I have negative 0.868. Negative 0.868. That's pretty good correlation. It's very close to 1. Use technology to find the equation of the least squares regression line. We've already done that. It's right here. Y equals negative 12.7 plus, or x plus 116. Let me write that out so you can see it better. Y equals the A value, which is negative 12.7 x plus, and the B value is 116. So there is my least squares regression line. Interpret the gradient and y-intercept of the least squares regression line. So this is the gradient, and this is the y-intercept. Basically, the y-intercept tells me that it's $116, maybe about here, I guess. And I would say that the line probably looks something like that, okay? So the $116 represents the amount of money used for fast food for the person who spends absolutely no time making homemade meals, okay? So I'll write that here. I'm going to write that a person who spends 0 hours making homemade meals would spend $116 on fast food. Okay? All right. That is the y-intercept interpretation. Now, what about the slope? The slope says for every hour you spend making homemade food, you save $12.70 on fast food. Okay, that's what that negative 12.7 would mean. All right, there's a rate of 12.7 hours saved, or $12.7 saved for every hour you spend making meals, homemade meals. Okay, all right. Now we go down to E. Another family spends 5 hours per week preparing homemade meals. Estimate how much money they spend on fast food each week. Comment on the reliability of your estimate. Okay, so now we can use the equation that we just found here. We can use this equation to figure out what would be the amount of fast food expense for the family that that spends 5 hours making homemade meals. We can find that by doing y equals negative 12.7 times 5 hours plus $116. And so to get that, we can just like use the calculator here, and we'll say negative 12.7 times 5 plus 116 gives us 5250. Okay, so that's our estimate for part E. Comment on the reliability of your estimate. Let's see. I think we could say it's a pretty good estimate. It would be a pretty good estimate. And there's a couple reasons we could use here. One is because we have a good R value. Our R value is 0.868, right? Very close to 1. It doesn't matter if it's negative. The reason why it's negative is because it's a negative slope. The 0.868 indicates that we're close to 1, which means it's a high correlation. So the linear regression line is a good estimate of the data. The other reason why we could say it would be a reliable estimate is because we are interpolating and not extrapolating, i.e., 5 is within our data cloud, or x equals 5 is within our data cloud. Okay? It's like x equals 5, it would be, around here, right? So that is within our cloud of data here. So it's interpolating. So interpolating is valid. Okay? All right, let's go to number 7. The quantity Q of a chemical responsible for skin elasticity is measured at various ages, T years. The results are shown in the table and in the graph. What is the effect on Q as T increases? Looks like Q decreases as T increases. So we'll say the effect of Q is Q decreases. Okay. Is the graph linear? It looks pretty linear, right? Looks like it. Construct a table of values comparing Q with square root of T. Now they're going to kind of tell us maybe it's not so linear. Okay, so let's make a table with another row, which would be square root of T. And I'm going to move this here over here. And then I'm going to move this to here. And then let's see. I'll put this up here. And so like instead of just T here, the square root of 2 is like 1.41. Square root of 10 is like 3.16. Okay. And so I'm gonna make square root of T values for each one of these. I don't know the square root of 20 by heart or anything, but so I'm gonna fill these up. You know, one of the easiest ways to do this is with the calculator. I'm gonna show you how the calculator can figure these out really fast. I'm going to use L1, L2, and L3. And so first I need to clear out each one. So I go up on top of L1, L2, and L3. I press clear, and that clears the whole column. Okay. Be careful, don't press delete because that deletes the list, and it's kind of hard to get it back. Okay, so I'm going to put this data in here first. I'm going to put 2, 10, 20, etc. Okay, and I'm going to put that data in L2. 2, 10, 20, etc. And then for L3, I'm going to put 119, 98, 119, 98, and I'm going to pause so that you don't have to watch me type in all this data. Okay, I've entered all my ages into L2, and I've entered all my chemical levels into L3. And now I'm going to show you the cool part. It says it wants to know the square root of t values, and I've been doing these by hand. But guess what? The calculator can do these automatically. And the way you do that is you go to the L1. When you go to L1, it says L1 equals. So now what I'm going to do is I'm going to make L1 a formula that is going to take L2 and square root it. So I'm going to say L1 is equal to, and then I'll say square root of L2. And look at that. It fills in L1 with all the square roots of L2. So that's exactly what I started doing here by hand. 1.41, 3.16, and so on. Isn't that cool? Okay, so construct a table of values comparing Q with square root of t. I just did that. If I want to like write each one, square root of 20 appears to be 4.47. Square root of 30 is 5.48. Square root of 50 is 7.07. Square root of 65 is 8.06. Square root of 80 is 8.94. Okay. Made a table. Okay. Explain why Q equals M square root of t plus c is a likely model for the original data. Well, let's see. I'm going to test two things. One is I'm going to do a stat calc lin reg for the original data, which would be L2 and L3. Remember, this is L2. So I'm going to put L2 and L3. And then I'm going to see what the R value would be for that. The R value for doing L2 and for T and Q would be negative that. So I'm going to say, okay, T and Q. The R value is negative 0.976. That's pretty good. That's pretty good. Now let's compare that with square root of TQ. And the way we would do that is we would go to stat calc, and instead of putting L2 and, stat calc lin reg, instead of L2, L3, we're going to do L1, L3. And then we're going to check to see what we get for R now. Wow, look at that. Now we have an even better R. Now R equals negative 0.9997. You see how like R is even better than it was before. So yeah, the reason why we think that square root of T and Q are the linear relationship and not T and Q is because the R value is even closer to 1 than when we did T versus Q. Okay? Alright, so that's D. E, use your calculator to find M and C. Okay, we already did that. Here it is right there. We're going to say Y equals negative 11.9x plus B is 135.4. Okay? This is M, what they called M, and this is what they call C. Find the quantity of chemical in a newly born baby and a 25-year-old. Okay, so a newly born baby means the age is 0. So if and remember, this x here is not really t, it's square root of t, right? So remember that. So what we have here is negative 11.9 square root of t plus 135.4. So let's say, okay, for a newborn baby, we're going to have y equals 0 plus 135.4. The value is going to be 135.4 for a newly born baby. Okay. And then for a 25-year-old, what about for a 25-year-old? Well, they picked 25 because the square root of 25 is 5, so it's easy, right? So for this part, we're going to have y equals negative 11.9 times 5, because the square root of 25 plus 135.4. And we can figure that out here. We're going to put negative 11.9 times 5 plus 135.4. We get 75.9. Okay, so that's for a 25-year-old. Are the answers in F likely to be reliable? Let's see. One of the answers that we're estimating here is like 0, 135. That one right there, right? Actually, it's not this line. It's a different line, right? Because this is with t. We're gonna have a different graph where it's square root of t and q, and it's going to be a straight line, and this is going to be 135. So we have one data point we estimated right there, which is this one. And then we also have this one, which is 5, 75.9, which is right there. And you can see that 25 is in the middle of our data, right? 25 would be right there, right? 0 would be here. So the question is, which of those, if either one, is going to be accurate? And we would probably say that the point 5, 75.9 is more likely to be reliable because it is interpolating and not extrapolating. 0, 135.4 is extrapolating, so might be less reliable. However, the R value is very close to 1, so probably both are reliable. Okay, remember the R value was like super close to 1. It's negative 0.9997, right? So we can be pretty safe about it. We can feel pretty good about that. Okay? I would like to move this down if I could, but I can't figure out how to. Okay, so, but that was it. This is the last one for this problem set. I hope the other two you're going to be okay on because they're very similar. Basically, you're just doing everything on the calculator. You just need to understand how to use the calculator, and you got to do several problems to get to the point where you're comfortable with it and you've memorized all the buttons and stuff. That's it. Thank you.